Let's talk about LSTMs, special memory systems in AI. To understand why they matter, think of characters like Lucy from 51st Dates or Sanjay from Gajini. Both suffer from short-term memory loss. Lucy forgets each day, Sanjay forgets every 15 minutes. Without reminders or notes, they'd be completely lost. Basic AI models, like regular RNNs, have the same problem. They process information step by step but forget things from earlier, just like Lucy or Sanjay without their memory aids. That's where LSTMs come in. They're like the tools those characters used, videos, tattoos, photos, to remember what matters. LSTMs don't just store everything, they decide what to forget, what to keep, and what to use. So when Lucy wakes up, she doesn't need to remember what she ate. She needs to remember Henry. That's exactly what LSTMs do. They filter out the noise and hold on to the important stuff. Thanks to LSTMs, they give AI a smarter kind of memory. Now that we get the idea behind LSTMs, let's quickly look at how they actually work. An LSTM is a smarter version of an RNN. Regular RNNs forget things too quickly, like Lucy or Sanjay without their memory tools. LSTMs solve this with a memory system and three key gates that control what to keep and what to forget. Forget gate. Like Lucy ignoring what she had for dinner, this gate filters out unimportant data. Input gate. Like Henry's video or Sanjay's tattoos, this gate decides what new information to save in memory. Output gate. Just like Sanjay focusing on a clue in the middle of a fight, this gate picks what part of the memory to use right now. These gates work together to help AI remember what matters over long periods. In short, LSTMs give AI the ability to remember the right things, just like Lucy and Sanjay's memory tricks help them make sense of the world. So, what exactly is an LSTM? At its core, it's a specialized variant of a recurrent neural network, or RNN, that's been designed to capture long-range dependencies in data. Whether you're processing sentences, time series signals, or audio, LSTMs help retain information over long intervals. Why LSTM? You might wonder, why not just use a vanilla RNN? The answer lies in the infamous vanishing gradient problem. Standard RNNs often struggle to learn relationships between events far apart in a sequence. LSTMs overcome this by using clever gating mechanisms that control the flow of gradients during training. This means your model can learn to remember or forget information over long spans, keeping critical context alive. Key innovation. So, what's the big innovation inside an LSTM? It's the introduction of memory cells combined with three regulating gates: input, forget, and output gates. These gates decide what to store, what to discard, and what to pass forward, allowing the network to maintain and manipulate its internal state effectively. Imagine an LSTM as a superstar personal assistant managing a busy executive's priorities. It knows which tasks to keep in mind for the long haul and which to let go. First up, the forget gate. Just like our secretary filters out unimportant emails and meetings, the forget gate discards irrelevant information from the cell's memory. Next, the input gate acts like adding new important items to the to-do list. It decides which incoming data deserves space in the memory cell. Finally, the output gate summarizes the day's work, deciding what information to pass along as the network's output, analogous to a well-crafted daily briefing. First up is the input gate. This gate regulates which new information gets added to the cell state. Think of it as deciding what's important enough to store. Next is the forget gate. It controls which information should be removed from the cell state, much like clearing out clutter to keep the memory clean. Then there's the output gate. It determines what part of the cell state is sent forward as the network's output, similar to summarizing the decisions made so far. Finally, the cell state itself acts as a conveyor belt, preserving information across time steps and carrying the memory forward. Three key natural language processing applications where LSTMs shine. First up, text generation. LSTMs enable chatbots and creative writing tools to generate coherent, context-aware text, whether it's drafting replies, storytelling, or autocomplete features. Next is sentiment analysis. By processing sequences of words and capturing long-range dependencies, LSTMs can accurately detect the emotional tone in customer reviews, social media posts, or survey responses. Finally, machine translation. LSTMs power many sequence-to-sequence models that translate text between languages. maintaining grammatical structure and context across long sentences. 3 natural language processing applications powered by LSTMs. First, speech recognition. LSTMs form the core technology in advanced systems, think WaveNet, and other state-of-the-art voice-to-text engines by modeling audio sequences over time. Next, music generation. By learning pitch, rhythm, and timing patterns, LSTMs can compose original melodies and harmonies, crafting music that flows naturally. And then there's emotion detection. LSTMs analyze tone, prosody, and cadence to detect speaker emotions, whether it's excitement, sadness, or neutrality, making human-machine interactions more empathetic. 3 popular LSTM architecture variations that enhance its sequence modeling power. First, bidirectional LSTMs. These networks process data in both forward and backward directions, capturing richer context from past and future time steps simultaneously. Next, peephole LSTMs. Here, each gate can peek directly at the cell state before making decisions, providing finer control over what information is added, retained, or discarded. Finally, convolutional LSTMs. By combining convolutional layers with LSTM units, they analyze both spatial and temporal patterns, ideal for video prediction, radar data, and other grid-based sequences. Now let's see how LSTMs are trained and optimized for best performance. First, backpropagation through time. Training an LSTM involves unfolding the network across sequential time steps and computing gradients at each step, so the model learns to adjust weights based on errors propagated through the sequence. Next, the key challenges: vanishing and exploding gradients. Even with LSTM's gating, gradients can still shrink or blow up over very long sequences, making training unstable without additional techniques. Finally, optimization strategies. We tune the learning rate, adjust the number of hidden units, and apply dropout regularization. These hyperparameter choices help the network converge faster, generalize better, and avoid overfitting. Now let's see how LSTMs are trained and optimized for best performance. First, repeat actions. Just like mastering a skill, LSTMs improve through many iterations, practicing over and over on your data until they get it right. Second, backpropagation through time. This technique lets the network learn from past mistakes by propagating errors backward across each time step. Third, avoid gradient vanishing. By using LSTM's gated structure and careful weight initialization, we preserve useful learning signals across long sequences. Fourth, the learning rate. Tuning how fast the model learns is crucial. Too high and you overshoot, too low and training drags on. We'll explore how LSTMs power today's most advanced time series forecasting applications. LSTM is a special type of recurrent neural network that excels at learning patterns over time. Unlike standard neural nets, LSTMs can remember information across long sequences, making them ideal for anything where past data points influence future outcomes. Stock prediction. One major use case is stock market prediction. By feeding an LSTM historic price data, such as daily open, high, low, and close values, the model learns to identify trends and temporal patterns. This enables traders and analysts to forecast potential price movements more accurately than traditional statistical models. Next up, weather forecasting. Meteorological data is inherently sequential: temperature, humidity, pressure, wind speed, all changing hour by hour. LSTMs process these sequences to capture subtle dependencies, helping meteorologists predict tomorrow's weather with improved precision. Energy use. Forecasting. Finally, energy use forecasting. Utilities rely on LSTM models to predict electricity and gas consumption based on historical usage patterns. We'll see how LSTM networks excel at spotting anomalies across critical applications. Anomaly detection leverages LSTMs to learn normal behavior patterns in sequential data. When something deviates from finance to networks to IoT, these models raise the alarm, helping teams react before issues escalate. Use case number 1: fraud detection. Financial institutions feed transaction histories into an LSTM to capture typical spending behavior. The model then flags unusual transaction patterns, like sudden high-value transfers, for further investigation. Next, network intrusion detection. LSTMs analyze continuous streams of network traffic, learning normal packet flows. When deviations occur, potentially signaling cyber attacks, the system alerts security teams in real time. Finally, IoT failure prediction. Sensor readings from devices, temperature, vibration, pressure, are fed into an LSTM. By modeling normal operating patterns, the network identifies early faults, enabling proactive maintenance. Let's break down how transformers compare to LSTMs and where attention comes in. First, attention mechanisms can be added to LSTMs to help them focus on the most relevant parts of a sequence. Instead of treating every time step equally, the model learns to weigh important tokens higher, improving performance on tasks like translation and summarization. Next, hybrid architectures merge LSTM's strong memory with the transformer's global context. You get the best of both worlds, long-term sequence retention plus parallelizable attention layers for faster, more accurate predictions. So, when should you choose each? Use LSTMs with attention for smaller sequences or when training data is limited. For large data sets and tasks that benefit from full context, like language modeling, transformers are your go-to. We'll now see the main challenges of LSTMs and some powerful alternatives. Limitations. First, LSTMs can be resource-intensive. Their complex gating mechanisms lead to high computation costs, making training slow on large data sets. They're also prone to overfitting, especially when data is limited, and their sequential nature limits parallel processing. GRUs. To address these issues, consider gated recurrent units, or GRUs. GRUs simplify the LSTM architecture by merging gates, achieving very similar performance with fewer parameters and faster training times. Temporal CNNs. Next up, temporal convolutional networks. By using causal convolutions and dilation, TCNs capture long-range dependencies while allowing full parallelism, making them both fast and scalable. Neural ODEs. Finally, neural ODEs offer a continuous time framework ideal for irregularly sampled data. They model hidden dynamics as differential equations, adapting naturally to varying time intervals. Thank you for watching the video so far. We hope you found it insightful. This segment covered long short-term memory, LSTM networks, a specialized type of recurrent neural network, RNN. We explored how LSTMs use input, forget, and output gates to regulate information flow, their applications, example, speech recognition, time series forecasting, and various architectures like stacked and bidirectional LSTMs. The discussion also included training methods, optimization hurdles, examples are computational complexity, and alternatives such as GRUs and transformers. By now, you should have a solid grasp of LSTM's role, advantages, and trade-offs in deep learning.